All right, I think this is the last video in this tutorial. Assumptions and missing data, maximum likelihood, and then I've got kind of grab bag of issues at the end here. So with maximum likelihood, it's a two-step process. The first step is that we want to fit our prediction model, and the code here, that model statement, it's feeding two different things. First is defining the depression variable. And within this package called Lavon, which is a structural equation modeling package and a very flexible package, uh, structural equation modeling software used to always be commercial. So a lot of things in this class and in other classes I couldn't teach because you need specialized software like AMOS or EQS or M+. The Lavon package, and there's another one in R as well that does that does structural equation modeling that I'm not recalling. Those both have really cleaned out that market, which is great because these are approaches that it should be available to everybody. So the way the code works, if you have the equal sign and the tilde, what it's doing is creating what's called a latent variable. You can just think of this as a composite variable for now. We won't go into latent variables. That's really something more for the multiple regression, multivariate course where we do cover that. And then we're simply predicting depression from abuse. And then to fit our model, the command is SEM model, which is the name of the model that we just made, the data, and then all this other stuff you can leave as is. To handle the missing data, literally the only thing you have to type here is missing equals ML. That's it. You can also use robust estimators when we violate data assumptions. Those are techniques that don't make the same assumptions about our distributions and stuff. We get a lot of output, and not much of it is very useful. First page here has nothing on it for us. The only thing that we can really need here is where it says z-value and probability. That's depression predicted by abuse. That's what we're after. So a lot of output for one single value. Again, that's a lot easier than it's a lot easier than having to do the diagnostic stuff with multiple imputation, which means that it's a lot less difficult to screw up. You can see it produces similar z-values. One advantage is that it's simpler, no diagnostics. You can't really screw it up. The only limitation that I would say is that it can't really deal with single item predictors that have missing data. It did throw out some of the abuse cases, and that's exactly why that z-value is smaller. It has a slightly smaller sample size. It needs multiple item measures and to work properly. So that's really the only limitation. That said, in this case, I would have used multiple imputation because it doesn't have that limitation. But this is a relatively uncommon limitation. All right, I wanted to get into a few interesting applications of what we know about missing data. The potential to deal with missing data in an effective and accurate way has led to a number of methodological developments. First, we have what are called multi-form designs. This is where a participant might come in and complete a subset of materials, say 60% of it. Gives you a data set that includes a larger number of items, reduces participant load. If we know we're able to really well predict those other 40 from the 60 that were answered, hey, look at that. We've shortened our survey. Two method designs. We combine an imperfect measure with a gold standard measure. We use both of the measures about 25% of the time. Then we know what the relationship is between the imperfect and the gold standard measure. That'll allow us to estimate the missing gold standard measures down the line. These fall under the general title of planned missing designs. Gaining a lot of traction in a variety of fields, particularly those where measurement is expensive, whether people have to physically come in to a location and sit in an MRI or something like that. These sorts of models really have done a great deal for those approaches. All right, I did mention that a lot of bad approaches persist. Why is that in psychology? Well, psychological science is supposed to be confirmatory. We state hypotheses, we perform an experiment, we ideally reject the null hypothesis. That focus on confirmatory means that we value statistical significance over everything else. And what that means practically is that you could rarely publish, it's changing a little bit now, but historically you could rarely publish non-significant findings. It just wasn't a viable option. Mean and regression imputation are both great tools for generating significant results. We saw that they both deflate the standard error. Regression actually inflates the correlations or the covariances or the effect sizes, however you want to think about that. So, there is an advantage to using these. Are you getting accurate results? No. Are you getting the sort of results that will get you published? Probably yes. So that's why these bad techniques persist. All right, so conclusions. A lot of bad strategies that are in common use for treatment of missing data. Again, just because it's published, just because you're in a lab and that's what the person you're working for doesn't mean it's right. Historical barriers to those best practices, needing expensive software, for example, that has crumbled for most applications. We no longer have that excuse. If you have missing data, it's maximum likelihood or multiple imputation all the way. Despite our advances, a lot of researchers remain ambivalent about missing data. Many of them reject the idea that we should fill in values for unknown responses. And there's a great quote from the scientist Heisenberg here. Whenever we proceed from the known into the unknown, we may hope to understand, but we may have to learn at the same time a new meaning of the word understand. So we really have to kind of shift our understanding about what is accurate, what is correct, in order to embrace these sorts of approaches. Oh, incidentally, this is it's this guy, this Heisenberg, not him, not this dude. All right, I believe we are at the end.